Hello, everyone, and Happy New Year. And yeah, we have a new year. Last Sunday was still last year, 2018, and I covered space-time, my criticism of Peter's notion of space-time and of the fabric of around an atom. And today I'm going to cover what we dealt with most in our debate, and that was the slit experiment. And first question comes up, what is a slit? In fact, one of the guys mentioned that, are you going to cover the slit experiment? Because that's what we spent most of our time on. And yeah, I was planning on doing that. I just wanted to cover some material before I got to that. And that's what we did last Sunday and the previous Wednesday. Anyways, what is the slit experiment? Well, the slit experiment is, in fact, I'll put here a quote by Feynman. It's a good place to start our introduction today. He says the following. He says, let me see if I can make it a little bigger here. Single photon, could be also single electron, by the way. Double slit experiment is a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which it has in it the heart of quantum mechanics. In reality, it contains the only mystery. We cannot make the mystery go away by explaining how it works. We will just tell you how it works. They're going to describe, they're not going to explain. In telling you how it works, we will have told you about the basic peculiarities of quantum mechanics. Okay? And essentially, you have an electron beam gun, and you can shoot an electron or a photon. If you have like a laser pointer also, you can do this either way. You shoot an electron, it goes through the double slits, and it creates the interference patterns on the screen. And of course, Feynman could not explain this. He was completely baffled and just had no explanation for this. To this day, there is no physical interpretation for the slit experiment, whether we use photons or electrons, okay? And the main question that pops up is whether they can handle one electron at a time, like Feynman says. Of course, if you can't explain it because if you're handling one electron at a time and you produce these interference patterns, well, obviously you're going to have a very hard time, explaining this, and with particles. And maybe that's what we should have done. Maybe the quantum people should have rejected the particle hypothesis. I mean, if they followed Karl Popper, Austrian philosophy of science, he said, if an experiment falsifies your theory, you got to reject the theory. And that's not what quantum has done. They did exactly the opposite. They stayed with a particle against all odds. All experiments, all of them, 120% of them, falsify the particle hypothesis. There's not one. Okay, hi. I have, all experiments in quantum mechanics, all subatomic experiments, all of them falsify the particle hypothesis. You cannot explain a single one with particles. Look at what I'm saying, okay? You cannot explain a single one. Especially all the classical experiments, the photoelectric effect, slit experiment, polarization, you name it. Not one can be explained with particles. You cannot explain magnetism with particles, magnetic attraction. You cannot explain gravity with particles. Particles cannot explain a single experiment that we've ever done in the history of life on Earth. And so if we are to follow Popper, Karl Popper says, the experiment falsifies your theory, you got to reject your theory. In this case, we're rejecting the hypothesis, the assumption that things are mediated by particles. Well, what's the story? The story is that instead of rejecting the particle, they incorporated it together with a wave. And they say, look, some experiments we will explain with a wave. And some experiments are observations we'll explain with a particle. And so they came up with this wave particle, neither of which can explain all experiments separately. And instead of rejecting both of them, they blended them into an unimaginable thing called a wave packet. That's what we have today in quantum mechanics. Okay, so Feynman obviously he was baffled. He could not explain the slit experiment with particles, classically, in other words, with corpuscles. And so Peter comes around. He brings this up in our debate, in our discussion, friendly discussion in general, I think. And he says, we know for a fact that we handle one electron at a time. We know that we're dealing with one electron at a time. And this is what he has. This is the picture that I took from our debate. And he said, we know that there is an electron that exists at a single point in space. I can detect a particle in a location. So we can say with a high degree of accuracy that it is particle-like. Okay, so that's his conclusion. And you can see if you look at that arrow that he drew, the blue arrow going downwards, on the right-hand picture, I've signaled it, I've highlighted it as a single electron. Okay, so he's saying that the emitter, the source, sends through the slit, through one of the slits, a single electron, and that's what they detect at the screen, or in this case, the detector. Okay, so he's saying he can handle one electron at a time. That's the issue. Okay, so where does he get this? Well, he sent me a paper that dealt with the Aronoff-Bohm effect. I thought that was a little too advanced for most people out there. I'm not sure people understood a lot of what he presented. It was maybe not the right place or the right time to do that. We should have started a little simpler. And one good place to start is Tanimura, not the paper that Peter sent me, but another paper that Tanimura wrote or published 3 years later. And this is his paper. This is the demonstration of single electron buildup of an interference pattern. By the way, Tanimura and his group did this in 1989. This is when they published this paper. And it was already done 13 years earlier by Merli, an Italian group, Merli and his team. And for some reason, they gave Tanimura the credit. But Merli really came up with this experiment first. Not that I vouch for Merli, by the way. I don't think either him or Tanimura handled one electron at a time. That's what I'm going to talk about today. And but this is what Peter believes. He believes that these experiments prove or demonstrate to him or make him believe that that these people handled one electron at a time. What's the problem? Well, right there you can see it. This is a portion of the paper, and I just put it up there for you to see. They talk about coherent electron waves from a sharp field emission tip were sent to an electron biprism. So what's the issue? The issue is that if you look at the picture on the left there, what you have coming from the top downwards, you have electron, but you have electron waves being emitted by a field emission tip. And I'll go over that in a second. It's known as an electron gun. Okay. And then at the screen, they detect interference fringes, which is way at the bottom there in the picture. Okay, so they're saying they sent waves and they collected a particle. Lazar, particle stuff is all clearly nonsense, but it's extremely hard to debunk facts. Yeah, we're not going to do politics. Let me show you that we can clearly and easily debunk what quantum is proposing. I'll show that today. So if you have a little patience, you'll see where I'm coming from. This is going to be all scientific, okay, by the way. Anyways, according to Tanimura's group, they emit electron waves and then they somehow collect single electrons on the screen. They find the interference fringes, okay? And you can see the field emission everywhere, electron beam, wave of wavelength such and such. So they're talking about waves, wavelengths, and for some reason these have the magical ability to convert or to morph into particles. Okay, so Peter thinks that because we detect, and Tanimura, by the way, and Merli all these folks, all the mathematical physicists, they believe that because they can handle, they see one hit at a time on their screen or on their detector, that they're handling one electron at a time. The contradiction comes with the fact that the emitter, the source, is emitting waves. Okay, so we have waves are emitted. What the screen receives or what the detector receives are particles. Okay, that's the first contradiction. But we're going to get more in depth into this now today. Okay, so that's where Peter gets his information. Here is Tanimura's setup in a little more detail. Okay. And he says electrons are emitted one by one from the source in the electron microscope. This is a lie. This is a lie. He does not emit one by one from the source. He's making an assumption that he does. He clearly states that he's sending waves out of the source. And in fact, that's what another paper that wrote about Tanimura's, that analyzed Tanimura's paper. I'm going to put this up for a second here. Here it is. No, wrong one. Where is it? Here it is. This is a paper that analyzed Tanimura's paper, all in favor of Tanimura, by the way, but he says that electrons are emitted from a sharp tungsten tip by applying a potential difference of 3 to 5 kilovolts. That's a lot of voltage, okay? Keep that in mind. That's going to be important. Between the tip and the first anode ring through an effect known as field emission. What the hell are they talking about? What is a field emission? Well, a field emission invokes an electron, what is known as an electron gun, okay? And this is an electron gun here. The definition or what they do with an electron gun. Electron gun, a direct current electrostatic thermionic electron gun is a hot cathode which is heated to create a stream of electrons via thermionic emission. Okay, so thermionic, they're going to create ions through heat, and they're going to emit these electrons that are popped out of their atoms. That's essentially what these people are doing, okay? Okay, so Tanimura, again, here's the setup. He says he emits one electron at a time. That's not true. He does not emit them one at a time. He detects them at the detector one at a time. He emits waves, electron waves, because in quantum, an electron can be a wave as well as a particle, okay? They pass through a device called an electron biprism, which consists of 2 parallel plates and a fine filament at the center. See, you can see the slit there. The double slit is formed between the 2 plates and the filament that stands between them. So what the electron beam does is go around the filament and within the plates. And that's going to be the double slit experiment. With this setup, he produced interference fringes, okay? And again, the source is going to be thermionic. It's going to create what people call waves. And then at the detector, he's going to detect one electron at a time, or so he thinks. Okay, that's going to be the issue. That's essentially what we're going to be looking at here. Okay, so what's the problem with this? The problem here is that we have 3 ways, three explanations, 3 physical interpretations of what electricity is. One we can call, I'm going to call it the classical way of generating electricity, of what is electricity. The other one is the quantum version. And then the other one is my little old rope model of what electricity is. And these 3 are totally different forms of viewing electricity, of what the mechanism is. If you had God's eyes, you could see inside a wire, what would you see? That's the issue, okay? Okay, so now let's imagine we have a chamber. Okay, we have a chamber. And on the one hand, you have gases coming into the chamber. You can introduce gases whenever you want into this chamber. On the other, you have an outlet through which you can pump all gases and all material that's inside the chamber. You can create a vacuum inside the chamber. That outlet goes to a mechanical pump, a roughing pump as it's called, also a rotary vane pump, which pumps it down to the -3 torr level. Then from there on, you can have a diffusion or a cryo pump it down to, say, the -7, -8. You can even go further if you have the time and the patience. But typically, like, I worked in the -7 range when I worked with these pumps. And so you can pump it down to -7 torr range. That's quite a big, that's very low, high vacuum, low pressure, okay? And that means you've evacuated the chamber of lots of the material that was in there, lots of the gas, especially water. Water tends to stick to all the surfaces. You got to heat it up, evaporate it, and pull it out with pumps. That's essentially what the problem is. Okay, so you evacuate the chamber, and but before you evacuate it, let's assume you have the chamber normal operating conditions. In other words, you have the air, ambient temperature, everything ambient, just normal, okay? You're going to run a current from the cathode to the anode, okay? We're going to run electrons. We're going to assume they're particles. We're going to run all these particles from the cathode to the anode, okay? And so, according to classical mechanics, you need a conductor. You need some kind of wire, some kind of conducting material to take that electron all the way from the cathode to the anode. You can't do it through empty, through vacuum, through total vacuum. This is the setup. Here I'm going to show it. This is the classical model. You have all these atoms, and the atoms I just put as being still. They're not really still, okay? But the point is, you can send electrons to the cathode, to the anode, even if you pump the chamber. You pump it down, and as long as you have atoms in there, you can send them through because you need a conductor in classical mechanics. It turns out that in quantum mechanics, you don't need a conductor, or they haven't decided whether they do or not. This is the setup for quantum mechanics. You have the electron gun, which allegedly heats up the filament or whatever you've got there, the tip, and it sends electrons over. The blue are these electrons, but it doesn't need atoms to transport them. The electron beads go through from the cathode to the anode. And so the $1 million question is, if you pump down the chamber, like in the first case, here you have again the classical mechanics setup. You have all these atoms there. If you were to pump it down so that you get rid of all the red balls, will you have a current flowing? That's the $1 million question. Will these blue dots, these blue balls, these electron balls, will they go from the cathode to the anode if you get rid of the red balls? That's the question. The red balls are the atoms, the blue balls are the electrons flowing from one atom to the next, and that's the flow of electricity according to classical mechanics, 19th century classical mechanics, okay? Quantum says you don't. Quantum says that you can just shoot them with a gun. We have an electron gun that shoots the electrons out, and they're going to reach the anode, okay? So we got a little bit of a problem here because if we can do this, if we evacuate the chamber of all gases, you would think that more current would flow because the mean free path is increased. Suddenly, these electrons are not bumping into atoms, ambient atoms. If you can produce a perfect vacuum, every electron should make it to the anode, every single one. This is what you would see, something like this. Where is it? Here it is. I think it's this one. Okay, yeah. Just got to make it bigger. Okay, so if we remove all the gases from the chamber, every atom in there, the electron gun, which is shooting electrons only, The electron should have no trouble reaching the anode. We should get higher current. That's what we should get. The current should increase. But that is not the case. That is absolutely not the case. The case is that, here we have it again. So this chamber here, this one here, is with all the gases in there, okay? So the electrons are bumping into all kinds of atoms, and most of them, or a lot of them, a lot of the electrons don't make it to the anode. If, on the other hand, you evacuate all the atoms from the chamber, the electron gun should be pouring, tons of electrons from cathode to anode. It's just as simple as that. If you pump down the chamber, the current should increase. And that is not the case. The case is what we see here, which is classical mechanics, that you need atoms to conduct electricity. You need a conductor. The official version today is that you don't need a conductor, or that every material, including space, empty space, totally empty space, ideal vacuum, all of them are simply different levels of conductors. That's the party line. That's quantum's party line. They say that everything is a conductor. It's just a question of how much voltage you want to put across that, that space. Okay, but again, if that is true, as quantum says, then if you evacuate the chamber, electrons should be pouring in at a higher rate, more of them. Instead of this, you would get this. Okay, I hope everybody understands that. You have more electrons flowing, your current should go up if you pump down the chamber. That is not the case. And we don't need to, I don't need to show you that. You can run the experiment if you want. You'll find all kinds of experiments that have been done. I did this every day, so I don't need to prove it to myself. But if you need to do it, go ahead and look it up. If you don't have your own vacuum chamber to do it with, run a current from one plate to another, pump down the chamber. Current will not go up. It'll go down. Guaranteed, okay? Let me tell you another here. I'll give you another version of that, and that's the open circuit. I guess most of you are familiar with this. You have an open circuit, and there's no light. In order to have electricity, you must close the circuit. And you say, well, why don't the electrons just go through the air, right? When you open the circuit, why don't they just go through the air and you still have light? Well, you can if the plates, if the two ends are close together, and you increase the voltage, with a resistor obviously in there so you don't burn the bulb, you can get current rolling if you increase the voltage. But for the same voltage, if you open the circuit, the electrons don't go through air. And believe me, they do not go through empty space. So, you've got many experiments, many observations, our experience that tells us that it is not true that electrons fly through space without some kind of conductor conducting them, without them going from atom to atom. Even assuming we accept the electron as a bead that orbits the atom, it doesn't happen, okay? And that automatically destroys the entire electric universe, because they believe the same thing. They believe that, they use Bohr's planetary model of the atom. The entire electric universe uses quantum atom, and they have these beads, the electron beads, and they fly from one galaxy to the other through empty space. They call it plasma, and plasma has this electricity flowing through it. No such thing, not in empty space. Electricity only goes through conductors. You need atoms. That's what a conductor is, a bunch of atoms, okay? And so what is my version? Well, my version is the rope model. Let's see if I can find it here. Here's electricity according to Bill Gates. Okay, it's all these atoms. They're connected. They're merged. Martin asked, did Peter acknowledge that this is not the case? Well, we didn't get to that far because, there were too many questions that were raised by by Peter, the overall discussion went like this. He sent me 4 papers, and he said those 4 papers debunked, or at least he wasn't convinced that the rope model could answer those 4 papers. And I analyzed that, I think it was last Wednesday. The papers just dealt with a bunch of concepts. So the first thing we had to do, that's why I wanted to get that straightened out with Peter first. I didn't, succeed in taking him in that direction very much. He was bent on putting his 4 experiments, but I wanted to get to the basics of physics. What is physics about? And I'm saying physics is about objects. Well, there were no objects in any of those papers. So we never got to analyze this part that I'm showing now, Martin. But again, I just want you to understand that if you have a chamber, just one more time, okay, and you have a current running with normal atmospheric pressure, and you have, a cathode and an anode, you're going to have a current there if the voltage is quite high, okay? So you run this voltage. Okay, you run this voltage. Now in fact, you can put argon in there, ionize the argon, which is what we used to do, and you can get a current running. Okay, but what happens if you pump down the chamber so that there are no atoms in there? There will be no current flowing. Quantum mechanics says the opposite, because they talk about an electron gun. They invented this in the 1920s. Okay. Several people worked on this, and they came up with this electron gun, which they think is an electron gun. And you have to think of it as as a gun, shooting bullets. That's what an electron gun is. That's what they think they're doing. They think they're shooting bullets from the electron gun by, it's called a thermionic emission. They heat the tip to high, with high voltage, they heat the tip, and they think they're emitting electrons from the atoms. That's what they think they're doing. And they think that these electrons, just the electrons, are going through space to the anode. That's what they think they're doing. If that's the case, if you pump down the chamber, the mean free path increases, you should get a higher current. That is not the case. 100%. 150% sure. You can talk to any person who deals with vacuum and electricity, and they'll tell you the same thing. You remove the material from the system, you got to increase the voltage if you want to arc, if you want to have some spark in there. Otherwise, there won't be anything going on. Okay, so you can take that to the bank. Okay. Electrons all by themselves do not travel through empty space, fully empty space. And just for your understanding, because there's a little more involved here, and I just want this to be on the record as well. These are vacuum levels. Okay, these are typical vacuum levels for different levels of vacuum. Atmospheric pressure is at 760 torr, and you can think of that as about 10 to the 19th particles per centimeter cubed. Now that's a lot of particles. What is a centimeter? A centimeter is about half an inch, a little less than half an inch. So it's a tiny bit like that, and if you take a little cube of that, right? You got in there 10 to the 19 atoms. Think about that. That's how small an atom is. A hydrogen atom is half an angstrom across. Half an angstrom. So the diameter. So you're talking about something extremely, extremely small here, right? And that's how much you can fit in one atmosphere. Okay, 760. Okay, so let me get the vacuum level again here. There we go. Vacuum tube, typical tubes, they run in the 10 to the minus 5 range. That's 10 to the 12 particles per cubic centimeter. Sputtering chamber, the one I use, 10 to the 7th, 10 to the minus 7, that should be a minus, sorry. Vacuum level, that's torr, right? And you got maybe 10 to the 9th particles, that's about 1 billion particles per centimeter cube. Okay, so you're talking about a lot of particles, even in a sputtering chamber that's been pumped down to what is known as high vac. That's high vac there. The moon has been measured 10 to the -8 to 10 to the -12. And there you still have anywhere around 200,000, maybe 300,000 particles per cubic centimeter. Interstellar space and intergalactic space are calculated. Intergalactic space, there was one study that intercluster medium, that's what they call the intergalactic space, ICM there, they came up with a number like 1 particle per cubic meter. So very low density in particles and gases. They think there's this plasma out there, but the plasma is so low density that there's really nothing there, essentially. That's almost pure vacuum, or that's about the best vacuum you'll ever get in the universe, you know, what's between 2 galaxies. We never measured that, it's too far away, we've never been that far. All we can do is say that when you evacuate a chamber, you got gazillions of particles still in there. That's why you still have current. If you could produce a perfect vacuum, there would be no current whatsoever. You need a conductor. The conductor is the gas that you still have in the chamber. In fact, that's what we did, you know, when we did sputtering. We brought down the chamber to -7 range, and then we filled it up with argon, took it back to the -3 range, which is, you know, lower vacuum than -7 range. So you take it down to high vac, and then you bring it back up to low vac, okay, or medium vac, you can say. That's where sputtering occurred, and that's where you can do something with it. Otherwise, you can't do anything with it. And okay, so the bottom line is that this is the model for the rope hypothesis. We have all these electron shells, they're merged. And again, I'm simplifying here because I've got an S shell here only. Think of that as a hydrogen atom. Obviously, you know, you're dealing with molecules, not with individual atoms. This is just to show you the, you know, the mechanism. That's all I want to show here. And what they're doing, the atoms are twirling. You have what I call a serpentine. All these atoms are interconnected, forming that whole red line. We're going to call it a serpentine. The serpentine twirls in place. Think of it as a drill bit turning in place. I think I showed you that last time. We had quantum mechanics, which does it with cannonballs. This is the quantum mechanical way. They make holes in the wall by shooting electrons across space. Okay, and you know, I'm suggesting that what's really going on is this, that we have a drill bit twirling in place. So we have a different mechanism for electricity, and the rope model is the drill bit twirling in place. That's what you see there. Okay, so that's electricity according to the rope hypothesis. Let's see, I've got here we got a better or a different version of that. And why I show this version is that you can see the electron shells are merged, but they swing around the threads that have come loose because of the high speed in which the electrons are twirling. They pull the threads out, or they push them out, and the threads swing around the serpentine there. And that's going to be the magnetic field. As you can see, electricity goes into your eyes downwards, and the magnetic field is at 90 degrees to the flow of electricity. That explains why when you take a circuit, you know, when you take 2 wires, they either attract or repel each other, being parallel to each other, depending on which way the current is flowing, because it's those magnetic lines, physical lines, which are interfering with each other. And I showed that in a different video. I'm not going to go over that right now, just summarizing there. So what is the slit version? But is it under the same as Perhaps not for this episode, but isn't electricity, I guess, under RH the same as electricity the same as magnetism? No, they're different, Martin. Just in smaller scale. Shells must spin clockwise or counterclockwise to transport current. We'll take you got to take a rain check on that. That's a can of worms that you raised there, but I can go over that in a future presentation, future lecture. Let me continue with this because I do want to cover a couple of things here, some ground. I hope we understand that there's three mechanisms that are on the table for what electricity is. One is the electron bead goes from atom to atom. You need a conductor. Conductor, we're talking about atoms. The other one is the electron gun, which Quantum invented. They said, you know, we can shoot electrons without any atoms to serve as highway. Okay, so just the electron beads. It's like the cars flying. You know, there's no highway, and the cars just go through air, I guess, right? And then the other one is the drill bit twirling in place. You know, so those are the three mechanisms on the table for electricity. The one you can reject for sure, 100% sure, is the quantum one. Why? Because no electron beads fly through space. Why can we prove that to ourselves or be convinced of that? It's because if you take electricity inside a chamber and you pump it down, the electricity should increase because the mean free path has increased. That's not the case. It's exactly the opposite. You remove material, current will go down. You need to increase the voltage. That's what happens. Okay. Okay. So I hope that is clear. That's the first part. And then what's the second part? Well, the second part had to do with. Let me get it organized here a little bit so that I talk a little more sense. We have. What was it? Oh, I just wanted to show, one more thing here before I leave this subject. And this is the rope version of the slit experiment using electricity, okay? I used the same setup that Tanimura had, and what you see there, I've just superimposed on that the serpentines, electron shells, which are, and again, these are molecules. Here using them as atoms, but I just want you to understand the mechanism. You can see the magnetic field there. Every now and then it's just going around the atoms, the serpentines. And what we're actually doing is simply sending one row of, not sending, but they're twirling in place. But what we're doing is having the atoms twirl in place around the filament, and that's being controlled by both the filament and the plates, which are either grounded or voltage is applied to them. So you can control the shape of the curve around the filament with those plates. And what we're saying is essentially we have matter there, and what's happening is that the electron serpentines, these atoms, these electron shells, which are merged one into the other, they're all twirling in place, and you can manipulate them any way you want. What I suggested many years ago now for some people to do who has the equipment is to put this entire system under vacuum. If you put it under vacuum, you're going to be removing electrons. And I'm saying putting it under vacuum, but don't increase the voltage. Just, do whatever you were doing. Get your current, get your, your fringes. But now just pump the chamber down and see if the current increases or decreases. That's all you got to do. And then you'll know for sure whether whether quantum is correct or not. Okay, whether quantum is on the right track as far as its explanation of the slit experiment. Anyways, we had a dialogue with Peter, and the issue was this fabric thing. He said the atom has this fabric around it, which prevents the electron from flying away. Because the issue was the following: if we're going to talk about the electron beads being detected one at a time, you must begin by showing me your atom, because apparently you're proposing a planetary model of the atom. In other words, you're saying there's a little bead somewhere around the nucleus. That's what you're saying. That's why you can move that bead, manipulate it one at a time, as Tanimura says, and shoot it against the screen or against the detector. So I ask him, well, what keeps the electron to the nucleus? What keeps the electron from flying away? And he said, well, there's a fabric. And I said, what is this fabric? He says, this fabric is, have you heard of a voltage? I said, yeah. I heard of a field also. Is that what you're referring to? Another word for field? No, a field is not the same as a voltage. And I'm saying, no. Is a field the same as a fabric? And he says, no, a voltage would be one description of what's going on associated with this fabric. So and he used different words. He said, well, it's a fabric of space. He said, it's a fabric of potential. He used all these words. None of them were a fabric of cloth. And so the question was, is there such a thing as a fabric of voltage, or can voltage be considered some kind of fabric? And, I hate to startle you, but no one to this day knows what voltage is. Okay, no one has any idea. No one can tell you what voltage is in physical terms. What is a voltage? You look up the word and you'll find the following definition. If I can find it here. Here's the definition. Voltage, electric potential difference, electric pressure or electric tension is the difference in electric potential between 2 points. Okay, and they usually simulate it with water. If you got lots of water on top and you got a little water on the bottom, well, there you have a difference in potential, and they call that a voltage. That's the analogy they give. They have no other way of explaining voltage. They just say, look, this is positive 5, and the other one is negative 5. Well, I did cover voltage a couple months back now. I'm going to bring up a couple of those pictures. And the first, well, let's go step by step. First thing we have to realize, because this is related, is that electrons spiral along a wire. Okay, when you have current flowing, the electrons are known to spiral. It's known as Fleming rule. If you have a magnetic field and the electrons are going through that magnetic field, the electrons will spiral. And that's what you have along a wire. Okay, that's the first picture. Now let's look up the dynamic version of this so that you can get an idea of how electrons move along a wire. That's essentially how they move. They move like in a circular or spiraling way. Okay, whether they move forward or not, that's a separate issue, but they do go around. Okay, that's how they move. Okay, and that's been verified by many experiments, and that's what we call knowledge. Okay. Okay, so here is my setup for the battery. Remember a couple months ago I talked about the battery. Here's a battery. This is typical, one of the original batteries, a lead battery. And you have on the right-hand side the negative pole, and the electrons, electricity, that's what you're seeing there, are spiraling. I hope I did a good job there, or as best as I could. You have to think of those electrons as spiraling around that green wire, okay? From the negative pole to the positive pole, okay? And the question is, why do they spiral? And what does this have to do with voltage? What is voltage? Is it just a difference in potential? And what is that? What do you mean a difference in potential? So what we do is we show the Rove hypothesis version of this, and all the atoms are interconnected, and what you have is that on the right hand side you have clockwise motion of the serpentine that goes all the way around, and it had better end up as counterclockwise at the other end. And that's what voltage is. Mother Nature doesn't understand minuses and pluses, 5 volts and minus 5 volts. She doesn't understand that stuff. She never went to college. She understands clockwise and counterclockwise. That's baby stuff. That's kindergarten stuff. We all understand that. That's mechanical. That's physics. And so what we have is the entire serpentine going around. All these atoms are interconnected. They're really molecules, but Here I'm just simulating with atoms because it's easier to explain. And what we're saying is that voltage is simply clockwise on one end and counterclockwise on the other. That's all voltage is. Okay, you give it a stimulus and that's what you get. Okay, so why is this pertinent to what we're showing here? Let me get myself in there again. It's pertinent because of the following. An atom does not look like a bead going around a nucleus. An atom looks like this, which is what chemistry has been using for hundreds of years. Well, I'd say several decades, maybe 100 years. This is what the chemists use to do atom-to-atom bonding, hybridization, and so on. These are atoms. This is what an atom really looks like. You have the S shells, the P shells, you have merging shells, and the quantum folk, they treat all these as orbitals. They say, oh, these are orbitals. And so you look up and say, well, what is an orbital? Well, an orbital is a region where you can find the electron bead. Okay, that's fine up to that point, but the problem comes next when they say that the orbitals merge from two atoms and they form a molecule. What do you mean the orbital? I thought the orbital was a region. And what is a region of what? You know, what is this? Is this a membrane? And yes, under the Rope model, this is a membrane. What we're looking at is the actual atom. We're looking at balloons. That's what an atom is according to the Rope model. So we're consistent with chemistry. We're very consistent. We're saying these are not orbitals. These are balloons. And what Schrodinger's equation does is give you the shape of the balloons. That's what his equation does. Quantum, on the other hand, says, well, what Schrodinger's equation does is give you a point, you know, in somewhere in the orbital. And yeah, because that's what an orbital is. It's a balloon. So they're looking at points all along the balloon. That's what they're doing. And so Schrodinger's equation is a way of drawing point by point the p orbitals, the s orbitals, you know, d orbitals, and so on. And then you're drawing orbitals. Okay? So if that's the case, then obviously there is no electron bead that can go, you know, from a source to the detector or to the screen. And again, you got to think about this, because if the electron is a bead, as they say, why would it come out as a wave? And you got to keep in mind that both the photon and the electron, they travel, the quantum says this, okay, this is not me, okay? It travels as a wave, and it only becomes a particle upon contact, at emission and at reception. But in between, it travels as a wave. And so, you know, when these people say that they emitted an electron bead, no, what's traveling is a wave. And then they bring their magic wand at the last moment, they convert it into a bead, into a little dot, a little particle, a corpuscle. And now they say, see, what hit the wall or the detector is a corpuscle. But that's magic. They haven't explained. What they need to explain is the conversion. What was the mechanism of morphing wave into particle? That's what we want to know. Because if you have an explanation for that, fine, then we've got it made. But of course, that's magic. Because the wave is extends throughout the universe. It's a field, and a field extends throughout the universe. Particle is concentrated. It's a point. How did this thing that covers the entire universe suddenly, you know, collapse, as they say, the wave function collapse? How did it collapse and become a particle, a little point, a little corpuscle, a vibrating field or localized portion of the field? They can't explain it. That's the issue. And so they, you know, that's why people like Feynman says, you know, we don't understand. Don't try to understand it. Just we'll just describe it to you. We can't explain it. That's the issue. The issue is they cannot explain. With the Rope model, we can explain it because it is a physical mechanism. We had better explain how Mother Nature runs her universe, and we have to do it with particles, with something solid, with objects. That's what we have to do it with. Okay, so what can we conclude from all this? By the way, here's a blow up of Peter's atoms so that people don't accuse me of putting words in his mouth. He does think of an electron as a bead that's tied to the nucleus, and the question, what is the gray stuff that separates them? That's what we want to know. We want to know what that gray stuff is. And that's the question that no one in quantum can answer, okay? And so Peter, what he did was he took his rag and he says, look, this is what it is. It's a rag. And on the right side, you see that area I circled there, irregular shape there. These lines that he drew, he says, well, it's this potential. Potential of what? And it's a potential of voltage, or that the voltage is associated with a potential, which in turn he says it's a rag or it's a fabric. So he turns the word potential into the word fabric to give it some physicality. That's all he did. And that's cheating. There is no physical object in quantum mechanics. He should know that. So he should not try to explain from a physical standpoint what keeps the electron from flying away, because quantum does not have an explanation for this. And in order to have an explanation, they need an object. And they don't have one. So they don't know what separates the electron bead from the nucleus. And that's the only question one of the most important questions that quantum mechanics has to answer. Okay, so summarizing here. Let's look at the conclusions we get from all this. See if I can put this up here. Okay, these are the conclusions. Conclusions, the electron gun misleads mathematicians to believe that electron beads fly through vacuum. Never happened, never will. An ideal vacuum, 0 particles, right, is a perfect insulator. You can't send electron beads through there assuming electrons were beads. Electricity requires a conductor, and a conductor means atoms. If electricity consists of a flow of electron beads, the proponent must illustrate the atom. Okay? Otherwise, we don't know where you got this bead. The bead obviously is something that is orbiting or is somewhere around the nucleus. Okay, so please draw your atom so that we know what you're talking about. If the theorist illustrates the electron as an orbiting bead, he needs to illustrate the medium that prevents the bead from flying spontaneously out of the atom. That fabric that Peter talked about. He needs to identify that unambiguously. Okay? No excuses there. Otherwise, he's not doing physics. Otherwise, he's doing abstracist. Neither potential nor voltage qualifies as a fabric or as a physical medium. Voltage is not a physical object. Voltage is a concept. You need to tell me what voltage is, how it's produced physically in order to talk about, physical interpretation. Otherwise, you don't have a physical interpretation. Voltage is defined as a difference in potential. That's what a voltage is. Therefore, mathematical physics has no physical interpretation for voltage, okay? Because voltage is a concept. It just means a difference in potential, and you cannot say that's a fabric. And if voltage is not a fabric and neither is potential a fabric, then don't use the word fabric, because all you're trying to do is insert it there without any justification. Therefore, it is irrational to state that a concept such as voltage binds the electron bead to the nucleus of the atom and physically prevents its departure. You cannot use voltage as a physical object. Claims that lab technicians have handled one electron at a time are assumptions. Claims that the slit experiment was performed by sending one electron at a time cannot be regarded as scientific until the theorists illustrate their version of the atom. You need to show me what your atom looks like to see if the bead is there. And if the bead is there, just tell me how it stays close to the nucleus before you emit it. Okay? That's the first step. If you can't do that, you don't have a theory. We won't listen to your theory. You got to illustrate that. And the last point, the quantum physical interpretation of the slit experiment is unscientific because the electron is regarded to be a wave at emission and a particle at impact. Quantum does not explain the mechanism of this magical conversion. Okay? And once again, the main point I wanted to get across today, and it's these pictures, these GIFs that I've got here. And that's, where is it? See if I can find it. Electricity according to, well, let's go with the classical first. Here's the one for classical mechanics. Okay, this is the one for classical mechanics. You need atoms to convey electricity. You can't do it without atoms. If you pump the chamber down, supposedly the electrons go with your atoms. You won't have a current flowing if you remove every single one of those atoms out of there. Okay, quantum says something different. Says that if you heat an electron gun, all these electron beads go across and they don't need atoms to go through. If that were the case, then if we pump the chamber down, we should get more electron beads going across. We should have a higher current. That is clearly not the case. Okay, that's falsified completely by experiment, if we're going to use the word falsification. So that's a lie. Never happened, never will. You cannot send electrons through the air, through a vacuum, through total perfect vacuum. And then what do we propose instead? We propose, if I can find it here, I'll get it here somewhere. I lost it. Got so many of these, you know. Give me a minute here. Oh, here it is. And here's the version of the rope model. That's that you do need atoms, you do need a conductor, but the conductor itself is electricity. All the molecules are spinning in place, in situ, and they could be air molecules, they could be water molecules inside the system. If you pump the chamber down, you will not have current. So classical mechanics and the rope model agree. They both disagree with quantum mechanics, which says you can have electrons without atoms. No, it doesn't occur. Electrons don't flow all by themselves, especially through the vacuum. Okay, so those are the main three ones, and that's the main point I wanted to get across today. So Peter has to justify that the detector detected one electron at a time. That is not true. That's his interpretation. There's no justification for it, first of all, because he needs to draw his atom first, and second, because even if he could draw the atom and say, look, the electron bead is held by God to the nucleus, okay, or by angels, fine. So the electron bead is held by angels. Now we heat the angels up and they release the electron bead, fine. If that were the case, then we have that scenario inside the chamber. If you have electricity flowing from one plate to another, you pump down the chamber, electricity should increase. That is clearly not the case. That also debunks quantum mechanics. And we should follow Popper in this case and say, yeah, if the experiment shows that your theory is incorrect, we got to get rid of the theory and not force fit it, in there at all costs. Okay, so once again, Happy New Year to everyone, and this is how we start the year. Hopefully, I'll see you. This coming Sunday, and might cover some of the issues that people brought up. Okay, we'll see you on Sunday. See you then. Bye-bye.